chapter 13, we're going to start talking about a different way to locate points in the plane. So the way we've been identifying points in the plane is with a pair of coordinates, x and y, which are called Cartesian coordinates or rectangular coordinates. So for example here, trying to locate this point P, how do we describe this point P in the plane? Well, we start at the origin. So we start at the origin, and the first coordinate is how far left or right we are from the origin. So the x-coordinate here, is -3, because to get to this point, I'm going to move 3 units to the left of the origin. The y-coordinate is 4, because this point is located 4 units above the origin. So we can get to this point by starting at the origin, moving left 3, and up 4. Or I could start at the origin and move up 4, and then left 3. And I would get to that point. So they use the adjective rectangular to describe this coordinate system because the motions of the system are left and right and up and down, which forms a little rectangular motion there. The coordinate system we're going to look at for the next couple of sections is called polar coordinates. Polar coordinates has 2 motions as well to get to a point. We're going to start at a point called the pole. So the pole is sort of the analog of the origin. That's our starting point. But to get to this point in polar coordinates, instead of going over and up, we're going to head out from the pole and then rotate around. So the heading out from the pole, that's the R part. Spoiler alert, R stands for radius, but R is more than a radius. But R kind of tells you how far out you're going. What's the radius of the circle that the point is on? And then theta is the rotation, the counterclockwise rotation from what's called the polar axis. Okay. So we still have 2 motions, but they're out and rotate. So we start at the pole, we head out along the polar axis, and then we rotate around to get to the point. So it's an out and rotate motion. So let's say you wanted to plot a point with coordinates 4, 5 pi over 6. All right, so here's sort of sketched out one way to do it. Start at the pole. R is 4. That tells you how far out you're going from the pole. So you go 4 units out from the pole, and then you rotate 5 pi over 6 radians, and that gives you your point. So you've gone out 4 and rotated 5 pi over 6. Or you could visualize starting at the polar axis, rotating 5 pi over 6, and then heading out 4 units from the pole. So just like with the x and y coordinates moving left and right, up and down, it doesn't matter the order in which you do those motions, you'll get to the same point. That's how it is with polar coordinates. You can either move out and then rotate, or rotate and then you move out. Now, R is considered a directed distance. We think of R for radius because it's going to tell you how far out you go, but R could be negative. If R is negative, that just means instead of moving to the right along the polar axis before you rotate, we're going to move to the left. So starting with -3.5 starts at the pole and then rotates pi over 4. And that would get you to here. So a negative R value means we're just heading to the left first. Or we could rotate pi over 4 first, and then instead of heading out from the pole this way, we'd head back through the pole the other way, 3.5 units. So negative R means we're just going the opposite direction as opposed to the positive R. But you're still going to be on a circle of radius 3.5. So the absolute value of R still tells you your distance from the pole. Now, if your theta is negative, that just means you're going to be rotating clockwise instead of counterclockwise. So If we want to get to the point 3.5 comma negative 3.4, we start at the pole, we go to the right 3.5 units along this polar axis, and then we rotate clockwise negative 3 pi over 4. Or we could start along the polar axis, rotate 3 pi over 4 clockwise, and then move out 3.5 units. Now, if you look at these last 2 points, ended up in the same spot. All right. If you look at this here, all right, if you look at this point, there's lots of different ways we can get to it. So this is one way to get to this point. The other way we got to this point is we went out 3.5 units and then rotated negative 3 pi over 4. Right? Or, and you might see this coming a mile away, you could add or subtract multiples of 2 pi to get coterminal angles to get to the same place. So for example, you could look at 3.5. If I add 2 pi over 4, I'd get to 5 pi over 4. So I would go out the same amount. Let's do it this way. I'd go out the same amount, 3.5, but then I would rotate 5 pi over 4. And that would get me to the same place. So that's one of the big things about the polar coordinate system, which makes it richer, i.e. technically more complicated, than the Cartesian coordinate system, or the rectangular coordinates that we're used to. With rectangular coordinates, if I look at the point negative 3, 4 in rectangular coordinates, that's the only way to describe that point. All right? Any other way to describe that point, x comma y, the x has to be negative 3, the y has to be 4. With polar coordinates, there's infinitely many ways to describe any given point because of coterminal angles and because of positive r values and negative r values. The last thing I want to mention is how they describe the pole. So remember, the pole is sort of taking on the role of the origin here. And in short, in just a little bit, we'll identify the pole with the origin and the polar axis with the positive x-axis to get in and do some of our analytic geometry. But if you wanted to describe the pole would have an r value of 0. And it would have the theta value of any theta you wanted. Right? So for example, 0 pi over 2 in polar coordinates means you start at the pole, you don't go anywhere, and then you just rotate pi over 2. So you're just sitting and spinning there. Right? There used to be a toy when I was a kid called a sit and spin, which was a great way for us to burn off all kinds of energy during the long winter months. Look at example 1. In each example, we're asked to plot the point given in polar coordinates and then find 2 alternative representations. One which has r bigger than 0, a positive r value, and one that has a negative r value. So let's start here. Our first example, the point P, 2 comma 240 degrees. So here we've got the pole and the polar axis. If you look here, each of these, we've got the r values there. We can label these wherever you want, but we can do 1, 2, 3, 4, 5, for example, all right, for their r values. And for the theta values, every theta value here, if you go through the arithmetic, every angle here, the angles are divided up every 15 degrees. All right, so that'll help us out. So if we start at 2 comma 240, I start at the pole, and I'm going to go out 2. All right, so I would start here at the pole, and I'd head out 2 units. That means I'm on the circle of radius 2, and I want to rotate 240 degrees. So here we go. So we start off here. There's halfway around, that's 180 degrees. And then we want to go another 60 degrees, so that would be, 4 of those? 15, 30, 45, 60. There we go. And so this would be the point 2 comma 240 degrees. Right? So that's where we would end up. Now, if I wanted to get another representation for this point with a positive r value, so there's 2, which means I'm going to be on the circular radius 2, I can just add another 360 degrees. So I can start here, I can go all the way around 240 degrees, and then just go around another 360 degrees. Boom, and I'm back at the same point. So I can just add 360 degrees to that, add 1 revolution, and get to a coterminal angle. So what would that be? 600 degrees? Right? 40 and 60 is 100. 200, 500, 600 degrees. All right, so that'd be another one. Now, if I wanted a negative r value, I could start, and instead of moving here from the pole out 2 units to the right to get on the circle of radius 2, I'm just going to start the pole, move 2 units to the left to get on the circle of radius 2, and then I have to figure out how many degrees I'm going to rotate to get that way. So negative 2 comma. And notice that I'm just basically leaving off half a revolution, right? So I'm starting here at the 180 degree mark. So I just have to make up the 180 to the 240. So I can just take this 240 and I can subtract 180 from it. And that's going to get me 60, so negative 2, 60 degrees. Okay, and because of coterminal angles, now I can just start adding and subtracting 360 to all of these values, and I can get infinitely many representations for that one point. All right, let's move along here to the next one. We have p negative 4 comma 7 pi over 6. So once again, each angle increment here was 15 degrees. So 15 degrees, that's like a pi over 12. So let's start. P here is negative 4. That means from the polar axis, I'm going to go to the left 4 units. So I'm going to come out this way. I'm still on the circle of radius 4, but I'm starting here on the left, at the left-hand side of the pole. Now I want to rotate 7 pi's over 6. All right, so 7 pi over 6. So here we go. So once again, we're thinking in radians. Halfway around would be 6 pi's over 6, which is pi. Then I need to go another pi over 6. So another pi over 6 would be 2 of these pi over 12 increments, and that would land me right there. So that's minus 4, 7 pi over 6. Now, once again, I want to get 2 additional representations for this point. All right, so one way I could do that, if I wanted a positive r value, is I could start at the pole. I'm on the circle of radius 4, so that tells me my r value would be 4. And then I want to rotate. I could rotate clockwise or counterclockwise. If I rotate counterclockwise, I just have to make up this extra pi over 6 here from the polar axis. Right? So I don't need to travel this additional pi, which is 6 pi's over 6. I can just start here and rotate up pi over 6. There it is. If I wanted to get an additional point with a negative r value, negative 4, I could start here, and then I could add or subtract 1 revolution, aka 2 pi. So just for fun, let's subtract 2 pi from that. So 7 pi's over 6 minus 2 pi, that'd be 7 pi's over 6 minus 11 pi's over 6, 12 pi's over 6. It gives me negative 5 pi's over 6. So what would that be? I would start here at the pole. I'd move to the left 4 units, get me on that circle of radius 4. And then instead of rotating counterclockwise, I'd rotate clockwise. So rotate clockwise 5 pi over 6, I would end up at the same location. Okay. So once again, The positive R values and negative R values, they're off by half a revolution, either 180 degrees or pi. If they have the same R value, then they're going to be off by a complete revolution, either 360 degrees or 2 pi. Let's take a look at these next ones. Here we've got P is 11d7 comma negative 5 pi over 2. Now once again, we can scale this however we want. So if we're doing 11d7, what makes sense? Maybe these are all increments of 50. So, 50, 100, 150, 200, I don't know. But we're going to start here, and we're going to go out, get on a circle of that radius 11d7, and I'm going to rotate negative 5 pi over 2. All right? So the negative means I'm going to rotate clockwise. 5 pi's over 2, that's more than 2 pi, right? So if I start moving around here we go. That would be negative 4 pi's over 2, and then I would end up at a negative pi over 2, so I'd be right here. So that would be the point 11d7, negative 5 pi's over 2. If I wanted to have another representation with the positive radius, it would be positive 11d7, and I could just rotate counterclockwise. I could just go around this way, and I would end at 3 pi's over 2. All right, so I basically just adding a couple revolutions to this, right? A couple revolutions, couple 4 pi's over 2, I would get to 3 pi's over 2. And if I wanted a negative R value, I'd go out 11d7 units to the left of the pole before I rotate, and I could select, for example, pi over 2. But if you add or subtract any multiple of 2 pi to any of these angles, you're still going to get to the same place. Right? So the R, you get 2 choices, plus or minus, but theta, you get infinitely many. Our last example here, we've got P is negative 3 comma negative pi over 4. So the negative 3, once again, I start at the pole, and I'm going to move 3 units to the left. The negative pi over 4 means I'm going to rotate clockwise pi over 4. So that would be 3 of these, right? Would get me there. So 3 pi's over 12, right? So 1, 2, 3. Yep, that would get me to the point negative 3, negative pi over 4. If I wanted to get a positive R value, I could move 3 units this way, get on that circle of radius 3, and then I'd rotate around. And I've got that pi over 4 there, so this would be a 3 pi's over 4. Right? Once again, these angles are off by a multiple of pi. So I could get that way. And if I wanted a third one with the negative R value, I could go negative 3. I could add 2 pi to this, so I could go negative pi over 4 and then another negative 2 pi. I could do that. Or if I added positive 2 pi, I could go this way and then sweep around here. And that would give me 7 pi over 4. If I just added 2 pi that way. Okay. So if the R is the same, I can just add or subtract multiples of 2 pi, get the coterminal angle. If the R is opposite, then I add or subtract odd multiples of pi. But hopefully you get a good idea now of the motions of the system. It's out and rotate. So we kind of mentioned this as we were going through that example. But this is the theorem that tells you exactly what's going on. If you have 2 different representations for the same point, and assuming that the r's aren't 0. Because once again, we mentioned that if you're at the pole itself, any theta will work. Then you've got two cases. If the r's are the same, the thetas have to be coterminal angles. If the r's are opposite, the thetas are off by an odd multiple of pi. Okay, so hopefully that makes sense. If the r's are the same, the only way you can get to the same point is by going a complete revolution. If the r's are opposite, then they're off by pi, and then any revolution from pi, so any odd multiple of pi. So think of this as 2 pi k plus a pi. So it's the revolution. It's, you know, the pi is the half revolution going from a positive r to a negative r, and then the 2 pi k is the revolution once you get halfway around. So you can think of it that way. Okay, so here's what we do to kind of marry the rectangular system with the polar system. Is we just basically what we do is we identify the origin with the pole. So the origin gets identified with the pole, and the polar axis is the positive x-axis. Okay. Now, if we do that, you know, we've got our r and theta here. Then we know from, I guess it was section 10.2, all the way back to 10.2, that x is r cosine theta and y is r sine theta. X squared plus y squared is r squared, and the tangent of theta is y over x, provided x isn't 0. And if x is 0, then we're living on the y-axis, and we know what these thetas are. These are like the pi over 2's. Okay. All right, so here we, you know, as I mentioned way back, and I've mentioned since, the key to trigonometry always comes back to the Pythagorean theorem and the definitions on the unit circle. And so we're seeing that again here. So, in example 2, we're asked to convert each point in rectangular coordinates into polar coordinates with r bigger than or equal to 0 and theta between 0 and 2 pi. Use exact values if possible and round any approximate values to 2 decimal places. Okay. So, these are all in rectangular coordinates, and we want to convert them to polar. All right, so the first thing I recommend is plot the point. That'll tell you what quadrant we're in, because that'll help you figure out what the angle is. All right, so we've done this kind of thing. 2 comma negative 2 pi over 3. So that's going to be here somewhere in quadrant 4. All right, so we go back to our conversions. X squared plus y squared is r squared. And since we want r to be bigger than or equal to 0, we can take r to be the square root of x squared plus y squared. That should look familiar, right? I remember doing a lot of these problems back in chapter 10. So let's do that. So x squared would be 2 squared, y squared would be negative 2 root 3 squared. 2 squared is 4. Negative 2 square root of 3 would be 4 times 3, which is 12. Whoops. So that's square root of 16. Which is 4. So that's 4. So that tells me that this point is 4 units away from the origin. And now I have to figure out what the theta would be. All right, so now I gotta figure out what theta is going to be. All right, and I want theta specifically from 0 to 2 pi, so that's why I'm drawing it that way. So I go back and I get the tangent of theta is y over x, negative 2 square root 3 over 2, negative root 3. Do I recognize that? Yeah, the reference angle is 60 degrees, aka pi over 3. So I know that my reference angle here is pi over 3. How many pi's over 3? All the way around would be 2 pi, which is 6 pi's over 3. I back off pi over 3. So here's your 5 pi's over 3. So 4 comma 5 pi over 3. Now, if I want to check this, I can convert back to rectangular. Okay, so how can I do that? Whoops. So in polar, we had 4 comma 5 pi over 3. And this is how we can go back. X is r cosine theta. So that would be 4 cosine 5 pi over 3. Cosine of 5 pi over 3 is a half. 4 times a half is 2. Y is 4 sine 5 pi over 3. 4 times negative root 3 over 2, which is negative 2 square root of 3. And so, boom, we're right back to the point P that we're given. Example here, we've got Q negative 3, 3. So once again, first thing I recommend is plotting the point here in the plane. These are the Cartesian coordinates. So negative 3, we're living here in, negative 3, negative 3. Living here in quadrant 3. So to get my R, I'll take the square root of x squared plus y squared. Square root of negative 3 squared plus negative 3 squared. Square root of 9 plus 9, which is the square root of 18, which, as well, we can see right here, that's 9 times 2. So that would be 3 square root of 2. So that's my R value. So that means that this point lives on a circle of radius 3 square root of 2. In other words, the distance from the origin is 3 square root of 2. So that's my R value. So it'd come out 3 square root of 2 units. Now I have to see how far I rotate. So let's look for the tangent of theta. That's the y over the x. So negative 3 over 3 gives me a positive 1. Do I recognize that tangent? Yeah, that's a pi over 4 reference angle. But sitting here in quadrant 3, so that's 5 pi's over 4. So one polar representation for this would be 3 square root 2 comma 5 pi's over 4. Now if you want to check the answer, we start with the polar description r theta, 3 square root of 2, 5 pi over 4, and we work backwards. X is r cosine theta, which is 3 square root of 2 cosine 5 pi over 4, which is 3 square root of 2 times negative square root 2 over 2. And we go through the machinations here. Let's see what we get. We get negative 3 times square root of 2 times square root of 2 is 2. So we get right back to negative 3. Y is r sine of theta. So 3 square root of 2 sine 5 pi over 4. So 3 square root of 2, once again, times negative square root 2 over 2. And we get back to the same thing we had before. And so the xy is back to negative 3, negative 3. Let's take a look at number 3. R here is the point 0, negative 3. So once again, this is given to us in rectangular coordinates. 0, negative 3, that's right down here along the negative y-axis. All right. We could go through the calculations. The x is 0 here. But we can actually just, I think, spot check this, because how far away is this from the origin? It's right on the y-axis. So I know my r value is going to be 3. And what's going to be the angle? Between 0 and 2 pi, 3 pi over 2. So this is one, really any point that ends up lying on one of the axes, we'll just be able to do it without doing any sort of excessive calculations here. And we can check this pretty quickly. So this is our r theta. X is r cosine theta. 3 cosine 3 pi's over 2. The cosine of 3 pi over 2 is 0. 0 times 3 is 0. Y is r sine theta. 3 sine 3 pi's over 2. The sine of 3 pi over 2 is negative 1 times 3 is negative 3. So we're right back to xy 0, negative 3. Or S is the point negative 3 comma 4. Once again, first step, let's graph this here in quadrant 2. So negative 3, 4. So it's going to be in quadrant 2 here. That'll help us with our angle. First step, we figure out r. So to get a positive r, I can just take the square root of x squared plus y squared. So there you go. Square root of 25, which is 5. And now to get theta, I know that the tangent of theta is y over x. So 4 over negative 3, or negative 4/3. Now, that's not an angle that we recognize, right? That's not one of the common values for tangent. So I'm going to have to use the arctangent function. A couple different ways I could go about doing this. If I took the arctangent function as is, this would give me an angle down here in quadrant 4. So this would be the arctangent of negative 4/3. Now, arctangent's odd, so I can pass that out front. In order to get it between 0 and 2 pi, then I would just add pi to it. And that would get me an angle between 0 and pi over 2. So I could write it, this way, or pi minus arctangent of 4/3. Okay? Because that's another way to think about it. Another way to think about getting to this angle is you could look at the arctangent of positive 4/3. Remember, the arc functions of positive numbers give you reference angles. They give you the acute angles. So here's the arctangent of 4/3 in quadrant 1. And so to get to the quadrant 2 variant, you would want to go pi and then subtract that to get back to this. So either way, however you want to think about it, this would be your angle theta. So the r theta here would be radius 5, and then pi minus arctangent 4/3. Okay. Now, if I wanted to check, this gets us some nice practice going back to chapter 10 with, chapter 11 with the inverse circular functions. Because x would be r cosine theta, which would be 5 times the cosine of pi minus the arctangent of 4/3. All right, now, we already have a lot of this done for us because we know that the terminal point here is negative 3, 4. So we know that negative 3, 4 with a radius of 5. So for the cosine here, I would take the x-coordinate over the radius. So this would be 5 times negative 3 over 5, or negative 3. Y is r times the sine of theta, which would be 5 times the sine of pi minus the arctangent of 4/3, which would be 5 times the y over the r, which would be a positive 4. So we get negative 3, 4. You could also check all of these, like on Desmos for the decimal approximations, and you would see that they tie out as well. Okay. So that's converting from rectangular to polar and then converting back. All right. Once again, when you go from rectangular to polar, you ostensibly have two options for r, plus or minus, and you have infinitely many selections for theta, which is why typically they'll ask for specific ones. All right, the last thing we want to do in this section is look at converting equations back and forth. All right, so convert each equation in rectangular coordinates to an equation in polar coordinates. So this kind of leads into what we'll be doing in the next section when we graph things. But this equation here describes a collection of points in the xy plane. It relates the x and y coordinates. So this is a relation. And you may recognize this, hopefully you recognize this from your college algebra class. This is a circle. It's got a center at 3, 0 with a radius of 3. So it's a circle that looks kind of like this. You got 6 there, 3, and negative 3. Right? So it's actually a circle. So we want to say, okay, well, this is what things look like when you try to relate x and y coordinates to get a circle. What does it look like when you've got r's and thetas? Okay, so there's a couple different ways to proceed. One way that'll get you there in the end all the time is looking at x is r cosine theta, y is r sine theta, x squared plus y squared is r squared, tangent of theta is y over x. So if you can get these combinations to show up, then you could convert over to polar coordinates. So the one that'll work all the time is plugging x and y into here. X is r cosine, y is r sine, then expanding stuff out. If you happen to see these other two collections, though, things could go a little more quickly. But let's demonstrate the first technique here. Let's just sub in x is r cosine theta, y is r sine theta, and let's see what happens. So there's an opportunity here to do some algebra. So we can multiply this out, r cosine theta minus 3 times the quantity r cosine theta minus 3. So that would give me an r squared cosine squared theta minus 3r cosine theta twice. So minus 6r cosine theta plus negative 3 squared plus 9 plus r squared sine squared theta, and that's equal to 9. And I look for opportunities to simplify. I could subtract 9 off both sides. And now I've got r squared cosine squared theta plus r squared sine squared theta. I can factor out that r squared. And look what I get. R squared, or cosine squared theta plus sine squared theta is 1. So I get r squared minus 6r cosine theta is 0. Now, in much of what we do with graphing polar, you're either going to get r as a function of theta, or theta is a constant. We're not going to see theta as a function of r too much. So when you get down to this, we want to like look to solve for r. So notice we could factor an r out of both of these terms. If I think about solving for r, and as fate would have it, I have two things multiplied together that give me 0. So either r is 0 or r is 6 cosine theta. Now remember, r equals 0, that just describes the origin. That's just the pole. You start at the origin, you don't go out at all, and you just spin around. 6 cosine theta will actually give us r equals 0 when theta equals pi over 2 or any pi over 2 plus any odd multiple, or plus any multiple of pi, actually will get you r equals 0. So this is the one we would select here, because r equals 0 is going to come out from this. All right, we're going to recover that point when we graph this equation. We know that r equals 0 can't be all of it because we know the thing's a circle. We'll talk more about starting with this and graphing to get the circle in the next section. All right, let's take a look at B, y equals negative x. So we got r sine theta is minus r cosine theta. We could start that way. Now, one possibility is, if we wanted to try to figure out what's going on here, it looks like we'll be able to solve for theta, but if we add things to both sides, we can factor out the r like we did before. And we have one case is r equals 0, which once again, that just describes a point. Now hopefully you remember what y equal negative x looks like. That's a line. So we know it can't just be that. So what's the other alternative? Is that the sine of theta is minus the cosine of theta. All right. Well, where does that happen? Well, we could divide both sides by the cosine of theta to get tangent involved. Now doing this, we assume that the cosine of theta can't be 0. All right. But do we care about that in this particular situation? If the cosine of theta were 0, then theta would be pi over 2 plus any multiple of pi. If theta is pi over 2, that's getting us the positive or negative y-axis, which we're not interested in. So we could go ahead and just simplify this. The tangent of theta is negative 1, and just pick theta to be this angle. So we could pick, for example, 3 pi over 4, or 3 pi over 4 plus any multiple of pi would get us here. And notice in this equation, theta is fixed at 3 pi over 4. R can be whatever it wants, including 0. All right. So if I let R be whatever we want, all we have to do is rotate 3 pi over 4. If R is 0, we're going to get 0 back. If R is positive, we'll be heading off into quadrant 2. If R is negative, we'd be heading off into quadrant 4. Okay. So you'll see in general that lines through the origin are going to correspond to constant theta values, and we'll talk more about that in the next section. All right, let's take y equals x squared. This is a friendly little parabola, right? So we've seen this before. Let's see what it looks like in polar coordinates. Y once again is r sine of theta. X is r cosine theta. So I get r sine of theta is r squared cosine squared theta. And so once again, we can subtract things over and factor the r out. So r squared cosine squared theta minus r sine theta is 0. Factor the r out. R cosine squared theta minus sine theta is 0. And so we're always getting back to r equals 0 again, which we know isn't the end all and be all of this, because that just would give us the vertex there at the origin. Or we'd have r cosine squared theta is sine theta. And once again, we could divide both sides by cosine squared, assuming cosine isn't 0. You get r sine theta over cosine squared theta. Which, in calculus, you would recognize this pretty quickly as secant of theta, tangent of theta. Which looks, doesn't look all that nice, right? Clearly, y equals x squared looks a lot nicer than this. Whereas with the last two examples, r equals 6 cosine theta, that's a lot more direct than this equation. Like if I tried to solve y as a function of x, I wouldn't even get a function anymore, but this r is a function of theta here, so we'll talk about that in the next section some more. And y equal negative x, this involves two variables. Theta equal 3 pi over 4 just involves one. So I guess the moral of the story here is there are certain curves that are going to be much nicer. The algebraic structure of some curves just looks nicer in polar coordinates than they do in rectangular. All right, now let's go backwards. Convert each equation in polar coordinates to an equation in rectangular coordinates. So we start with r equals 3. Now we know that x squared plus y squared is r squared. So r would be plus or minus the square root of x squared plus y squared. All right. So we could substitute that in there. And then we could square both sides. That gives us x squared plus y squared is 9. Now to check the reasonable of this answer, let's think about r equals negative 3. R equals negative 3 would describe all points in polar coordinates with the r value negative 3. So you would start by moving to the left 3 units, and then theta could be whatever. Okay, so that would sweep out a circle of radius 3 centered at the origin, which is exactly what this equation does. We got theta equals 4 pi over 3. We know that the tangent of theta is y over x. So I could take the tangent of both sides of this equation. So the tangent of theta, the tangent of 4 pi over 3, where is that at? So that's over here in quadrant 3 with a pi over 3 reference angle. So that's positive square root 3. So y over x would be square root 3. Y would be x square root of 3. Now once again, if theta equals 4 pi over 3, I'm looking at all points where the theta is fixed at 4 pi over 3. R could be whatever it wants. If r is positive, we'd be sweeping out that part. R is 0, we'd be at the pole or the origin. And if r is negative, we'd be sweeping out this. So by golly, once again, constant theta gives me a line through the origin. And the slope there is the tangent of 4 pi over 3, which is square root of 3. So that tracks. Our last example here, C, r equals 1 minus cosine of theta. So let's see how we can try to get this back to x's and y's. So we've got some difficulty here. I know what the tangent of theta is. I know what r is, but I've got cosine there sort of sitting on its own. So one thing we could do is we could multiply both sides by r. Now doing this, are we multiplying both sides by 0, and is that going to affect the graph here? Well, notice that when theta is equal to 0, 2 pi, negative 2 pi, any multiple of 2 pi, the cosine is going to be 1. So I will get 0 back. So we're kind of undoing what we did in the previous example, where we'd factor out the r and say, okay, that's a special case. Here we're multiplying by r, just to help us get in some of these things. So r squared I know is x squared plus y squared. R would be plus or minus the square root of x squared plus y squared. And then r cosine theta is x. So I guess if I wanted to get rid of this square root, I could add the x over. I'd have plus or minus x squared plus y squared would be x squared plus x plus y squared. And then I could square both sides and get this interesting curve. Now this is one you're probably not familiar with what these look like. So let's fire up Desmos and let's just see what happens here. First off, Desmos understands polar coordinates. For example, you go to the wrench there, you can actually go down and look at your grid. Boom. Ooh, you can make it polar. Okay. We'll have use of this. We'll be using this extensively in the next section. But let's go ahead and graph y equal 1, r equal 1 minus cosine theta. When you do this, it's going to automatically convert. It'll automatically know you're talking about polar. So check it out. And we'll talk about why we're getting this shape in the next section. So don't freak out about that. But let's see if we can get this to match. We had this crazy x squared plus y squared equals x squared plus x plus y squared all squared. And boom, there we go. Look. Okay. So that reassures us that we did convert it over right. Now, if you look at the structure of these two functions, this is much easier to deal with than this one. All right. And so we'll be talking about, because we know how to graph these kinds of curves, right, in xy space. Like if this were y equals 1 minus cosine x, we'd be good to go. This one, not so much. Okay. All right, so that'll do it there for section 12.1.